if you want to unlock the secrets to time travel and get your
flux capacitor fluxing,
then pay attention, because we're going to be going over flux. Roll the intro.
Do you feel the buzz?
There are many different ways to describe flux, and many different examples of what flux can be. You may have heard phrases similar to,
"My stomach is in flux."
This is because the word flux has many different definitions. It is often used to describe a state of change, but for this class, we're going to be discussing it as the first definition, which is an action or process of flowing or flowing out. We can then create a more physics definition of this, which would be an amount of field that goes through an object or area. In E&M, we're going to focus specifically on electric flux. Though since the definition and understanding of flux is kind of in flux, we're going to borrow from some other examples and things to help us describe what electric flux can be like. So think about situations in which you have an area that is buffeted by something. In this case, when the wind catches the sail, it pulls the sail in a specific direction. That in turn pulls Moana. So we could look at the amount of wind that hits the sail. Since the wind wasn't hitting the sail when it was closed, that means that the amount of area that the sail has is directly dependent on the amount of wind that's able to hit it. And quite obviously, the direction of the wind versus the direction of the area of the sail also matters. If the wind is coming from a flat angle with the sail, then obviously no wind will hit the sail. So in order to describe this, we're going to use something called the area vector. The area vector is always perpendicular to the area or surface, and has magnitude equal to the area of the surface. This way we can figure out how much of the field overlaps with the area vector by doing the dot product of that field with the area vector. This gives us a non-vector quantity that represents the amount of area that overlaps with the amount of field, or a representation numerically of how much of the field is passing through the area. And this is effectively what flux is. So we'll get the equation that the electric flux is equal to the E field dot the area. This becomes significantly more interesting when the E field changes over the area. In that case, we just have to integrate the E field dot dA. For you Calc 3 aficionados, the S means that this would be over the entire surface, and would therefore indicate a double integral over the different lengths that define the directions of the area. For you not Calc 3 aficionados, this, you just relate dA to dr in some way, and then integrate over dr potentially. There won't be any problems that you need to use Calc 3 for, so you'll always be able to separate dA and turn it into a function of dr and integrate. An especially common case of when you'll have an E field that changes with area is when we're talking about the flux through a three-dimensional shape rather than some two-dimensional surface. In this case, we just find the flux through each individual surface area that is on the shape and sum them all up. Note that you'll have to keep track of your positive and negative signs. Since the area vectors will all point out from the shape, this indicates that a negative sign means field that's coming into the shape, and a positive sign indicates field coming out of the shape. We can see this in the simple definition for the dot product, which is simply the two magnitudes of the vectors multiplied by the cosine of the angle between them. So when the two vectors are facing opposite directions, the cosine of that angle is -1. And when the area vector and the field vector are in the same direction, you get +1. This means that if you have an outside field passing through an object that doesn't change, like that time Sophie stood up to the Witch of the Waste.
The door's over here, ma'am. We're closed.
Standing up to the Witch of the Waste, that's plucky.
The Witch of the Waste!
The total amount of flux through that object will be 0. This is because you'll have a negative direction due to one side and a positive direction due to another side, and the two will directly cancel. So in essence, you have the same amount of field in as out. Now you may be thinking, but that's not giving me the amount of flux going through the object. And you're sort of correct on that. In order to find the amount of field going into the object, you could simply only consider the ones going into the object. But for our analysis of electric flux, the amount of flux coming out of the object versus the amount of flux coming into the object will be vitally important. That's because a little something called Gauss's law, which we'll cover in our next video, is strictly related to the amount of charge inside of a surface. And that about does it for this one. It is a short video, but hopefully it helped you understand what flux is and how we can apply it to electric fields. In our next video, we're going to be looking at how this is useful to us in order to solve for electric field. So stay tuned, check out the next one. Don't forget to like, comment, subscribe. If you have any questions, feel free to leave them in the comments below, or ask me during class.